Hello, everyone, and welcome to Synthesizing Cyber Infrastructure Efforts of C4P and the EarthCube Community, a webinar series organized by C4P. C4P, Collaboration in Cyber Infrastructure for Paleo Geosciences, is an EarthCube research coordination network supported by the National Science Foundation. I'm Leslie Shee, and I'll be the moderator today. In today's talk, we have two presentations, each 20 minutes with roughly 10 minutes for questions. We want to keep this to an hour, so I'll be fairly strict about enforcing time limits, and we'll give each speaker a 3-minute warning. If you have any questions, send them through the WebEx chat window to Research Coordination Networks, and I'll read them aloud after the presentation. You can send in a question at any time. All presentations and follow-up discussion will be publicly archived on the EarthCube website and at the C4P YouTube channel at youtube.com/Cyber4Paleo. Today, our first speaker is Nick McKay from Northern Arizona University, and he will be presenting on GeoChronR and ChronRater, new tools for quantifying, analyzing, and visualizing the impacts of age uncertainty of time-uncertain geoscientific data. Our second speaker is Yolanda Gill from University of Southern California, who will be giving a presentation on the EarthCube building block GeoSoft, a community software commons for the geosciences. So, Nick, you have the screen control, so you can begin when you're ready.
Okay, thanks. Thanks for that introduction, and thanks for inviting me to present this today. So I'm going to be presenting on two different projects and products, one called GeoChronR, one called ChronRater. And I want to acknowledge some of my co-conspirators and collaborators, Julien Emile, who's my collaborator and co-PI on the GeoChronR project, and Daryl Kaufman, Hannah Sundquist, and Nick Velasio, who helped develop or led the development of the Arctic Policy and Transition Database and ChronRater, which came out as part of that project. So with that, we'll start. So first up is GeoChronR. So GeoChronR is a recently funded, we're in the first year of funding for a geoinformatics project through NSF, with me and Julien Emile as the leads on that. And so this is very much still in development, but here's the underlying motivation of what we're trying to do with this product that we're looking to develop. So the idea is essentially to create a platform in R that provides a streamlined workflow to go from take time uncertain geoscientific data, think paleoclimatic or paleoenvironmental, paleoecological data, go through this first step of, I think you can see my mouse here, of uncertainty modeling, which is usually sort of age depth modeling. There's a number of algorithms out there, many of which are in R, that we'll harness. And so you can go through and create a suite of ensemble members of equally realistic or comparably realistic ensemble members of age depth realizations. Then to take all of those ensemble members and propagate that through your analysis step, whatever the analysis you're doing on, not on your ages, but on the paleo-environmental data or whatever it is of interest according to your research questions. And then finally take the data that comes out of that analysis and provide options for effectively visualizing those results. So that's the model, is to streamline this workflow and to make this broadly accessible to people who are interested in quantifying how uncertainty in ages and depths in their record impact the conclusions they're coming up with based on the rest of the data that they're measuring and analyzing. So just to zoom in a bit more, here's this first step, and I mentioned this is an output of this is produced by a product called CLAM, which is written in R by Martin Blau, where it fits, it quantifies the probability distribution of radiocarbon dates in this case in an age depth sequence, and then fits a series of splines through them. And so each of those faint red lines is one reasonably probable spline that can fit through those, and where you see darker concentrations of red, that's where more and more splines are lining up. It indicates increased probability. So the idea is, these algorithms are now pretty widespread in the community. A lot of people use them, but the most common use is to run this analysis, which is pretty sophisticated, and then to take that best fit line, the median of those ensembles, which is something like the black line, there, and then use that for all your further analysis, and essentially ignore that full distribution that you generated so nicely in this CLAM program. And you can see in some cases, like this little inset that's highlighted, the median is actually not a particularly realistic choice for the distribution, and it'd be much more interesting, much more useful to take the full ensemble through the rest of the analysis, and that's where the next part comes in. So as part of this package, we're developing the tools to do the sort of simple things that a lot of paleoenvironmental and paleoclimatic work relies on, things like correlation and regression, EOF analysis, SSA, and more, and propagate that through using each ensemble member. And the and more part is a key part of this. Is it's an R, and we're hoping this will be we're aiming for this to be a community effort. So there's some analysis that you'd like to see in here that we haven't developed. Hoping people contribute that. And I'll talk a bit more about that later on. And so here's one example where you might want to say regress how much the relative amount of chlorophyll abundance in your sediment core compared to temperature at the lake that you're looking at. And instead of just having a single line and a single correlation coefficient and alpha and beta values for the regression, now you have a distribution of those that are distributed as a function of age uncertainty over here on the right. So here's one example of how you might visualize things. With higher order mathematics, the visualization becomes a bit more complicated when you're adding this uncertainty element and the time dimension for methods that don't necessarily have built-in ways of visualizing that. So here's an example for doing multi-channel SSA analysis on time uncertain data. So here, for multi-channel SSA, you want to show something like the time series associated with it, the phase, and the amplitude at each site. So here the amplitude is shown by the size of the circle, with the blue and red dots being the confidence intervals as a function of age uncertainty. And then the black sort of fan is the phasing, with the width of the fan showing the uncertainty associated with it due to the time uncertainty in the record. So here's an example of the visualization. So I'd like to quickly just run through as a case study for how this might work for a study for a single site. So I was involved in this project led by Brandon Bolt that was just published in the Holocene, looking at Krupa Lake, north of the Brooks Range in Alaska. And here was something like I was just describing. So Brandon noticed early on that there was this pretty tight relationship between this parameter that has to do with chlorophyll abundance in the sediment, RABD, and temperature near the lake. But there's time uncertainty in this part of it. So we were interested in quantifying how much that time uncertainty influences that regression, which is what you see down below. There's some sort of spread of regression slopes, and also of each of those stats associated with it, right? The row alpha and beta in the regression. And then because we now have this ensemble of regressions associated with age uncertainty, we can take this reconstruction, which extends back about 5,500 years and was a single line, and turn it into sort of a suite of reconstructions that sort of quantify the impact of age uncertainty on that reconstruction, both in terms of where they are in time here and in the way that age uncertainty impacts the regression itself. So this isn't just, the goal of GeoChronR isn't just to put error bars or increase the width of your error bars around whatever it is you're trying to analyze. It's to really get to that final step where you can go to your sort of final conclusions and try to quantify how much age uncertainty might be impacting those conclusions. So one thing that was remarkable in this Lake Krupa record was it showed a remarkable amount of century-to-century temperature change. And so one thing we were curious about and looking at study was how does the amount of century-to-century temperature change over the past 6,000 years compared to the 19th century to 20th century temperature change. And here we see that what the result, if you did that with just using the original, without accounting for age uncertainty, that's using the median there, you get a tighter, narrower distribution of those temperature changes in those black bars, and then the light blue bars show the distribution of temperature changes, which are spread out quite a bit wider if you account for age uncertainty. So here we can quantify exactly how the age uncertainty affects this conclusion in the study. So GeoChronR isn't just for single site studies, it's also really designed for data syntheses and quantifying how age uncertainty in a number of sites affects the synthesis product or synthesis question you're trying to ask. And it's also it's intended to be a community product and to be developed by the community so that these analyses are being enhanced and added to by people who are using GeoChronR. And so to do this, you have to have some sort of data standards and a data container which is flexible enough that, so that we can all be working with the same input and output data. So a lot of the work early on in this project has been developing such a flexible data container and a preliminary standard. So this is what Julie, McKay, and I have been working on quite a bit for this in the first half year of this project. And we came up with a container that we're calling linked paleo data. It uses linked open data, and it's extremely flexible. It's based on JSON LD, the linked data version of JSON, and it's a hierarchical format that lets you accommodate essentially any type of paleo environmental data. And we have a white paper out. It's available on the web, and we're seeking feedback on this data container and the preliminary data standard that we've put out there. And there's a link to that white paper on the event page through this RCN. Okay. So with that, I want to move on to ChronRater. And ChronRater is really is something that was Daryl Kaufman's brainchild that came up during the development of this Arctic Holocene Transitions Database project. So this was a large data synthesis effort trying to pull together a state-of-the-art database that covers the Holocene and the Arctic. And so here's a number of criteria. It had to be Arctic-ish, north of 58 degrees. Span the mid-Holocene, has some other constraints in terms of the resolution and the age control. And here's what we ended up with in this database, where all the filled-in symbols are the records that made it, and all the hollow symbols are the records we considered that didn't make it. So in total, there's about 160 that made it in, and another 300, I think, that were considered that didn't make it. And so, and among other things, we also included all the original geochronologic data in this database. And so all the red dots are the sites that we have the geochronologic data for in this database. And the black sites are those that either don't have geochronologic data or we included it for a different reason. And so we now have 110 or so sites with age control, but there's different ways. We like to be able to quantify that, just as in the last project, how this age uncertainty impacts some of our conclusions or impacts the results we're seeing in the database. So one approach would be do something more like what I just described for GeoChronR, where we're creating a bunch of ensemble age models for each 100 sites, and then trying to propagate uncertainty through all of that. That becomes pretty unwieldy pretty quickly. And with ChronRater, we were hoping to do something a bit more simple that lets us stratify these sites as a function of their age certainty. So that was the motivation. It's a simple scheme that accounts for, comes up with some sort of semi-quantitative rating that lets us sort of separate the very good age models from the poor age models and rank them accordingly. And one advantage of this being a semi-quantitative scheme is it lets us incorporate some of this more qualitative understanding, which you can't really encode into an age modeling algorithm like what I was showing you earlier. So Chron score. It's simple. It has 3 parameters, each of which I'll define here in a second. It includes information about quality and precision and the delineation. And so I'll briefly describe what goes into each of those things. So delineation is delineation of the down current trend. It's trying to measure just how well do the ages you have mark out a linear or slowly changing trend in sediment accumulation, with the thinking that if you have a well-defined, simple trend, you are better capturing that trend than if it's you have a bunch a real squiggly, rapidly changing trend that's much more difficult to quantify. So this is a function of the frequency of ages, their spacing, and like I was saying, how smooth that sedimentation rate trends are. So the last thing we quantified by using a spline. So here's just a few examples of what different sites in the database look like in terms of their delineation. And in the case of delineation, lower values are better. So this first one has a quite low value of 0.5. It has a lot of ages in those black circles that define a very smooth, slow changing trend. So that's what we're looking for. And you can see as we go up, here's that starts to decrease a bit. The spacing, like in the bottom right one, becomes a bit more sporadic, but it's still a pretty straightforward trend. And if we go to some further down, we see fewer ages, wider spacing, and a more abrupt changes in the trend. And then lastly, as that situation increases, the delineation score increases, and which deteriorates the total score. Okay, the second parameter that I want to talk about of those three is the quality. This one's pretty simple. This is one of the places we get to incorporate some of this expert judgment of what makes a good ages and what doesn't. So here there's two things. It's the proportion of ages that were rejected in the ages. So if you measure 10 radiocarbon ages and 2 of them are rejected, that'll be a 20% proportion of rejected ages. And then also looking at reversals. So it's both rejected and reversals counting against you for this P. And then M is this material type score. So this recognizes that the community knows that measuring radiocarbon on some materials gives you better results than measuring radiocarbon on other materials. So for lacustrine sediments, and I should point out that this ChronRater is really designed for sedimentary records, lacustrine and marine sedimentary records. So here higher scores are better. So 5 would be that you have a bunch of macrofossil ages that are also independently confirmed by other type of some other type of chronology. Whereas the worst would be you have a number of just pure bulk sediment ages which are prone to large uncertainties. Similarly, for marine sediments, we have a similar idea where it's the best case scenario. You have mostly whole monospecific forams in a well-constrained reservoir age, and the situation degrades for lower scores. So here you're able to input some information on sort of qualitatively how good is the material used to create the age model. Okay, and lastly is the precision of the ages, and this is just simply how, after you calibrate the radiocarbon ages, how big is the uncertainty. So all these 3 things go into here, and everything that we put in have weights attached to them. And so the idea is this is semi-quantitative and is most useful in the context of a database where you're trying to stratify records, and different users likely want to quantify these values in different ways to change the relative weighting of different parameters in ways that makes most sense for their project. So that's what we do, the ways that we use. And we got a distribution that looks like this. So we accomplished our goal of stratifying the records. We have about 2/3 of them greater than 0, 1/3 less than 0. And you can see the impact. So as delineation increases, the total score, as delineation increases, the total score decreases. As the quality increases, the total score increases, and as the precision is the least important parameter in the way that we weighted it, and as the precision increases, the total score also increases. So in the last couple of minutes here, I just want to sort of show what this looks like in the context of the database. So here's the distribution of Chron scores in the database, the Archer-Collison transition database, as a function of resolution. So you see this trend. So we arbitrarily gave true inclinized cores very high Chron scores, just because the chronologies are highly defined and we can't measure them using this ChronRater method. And then look at the rest of the records, and we see there's this distribution. Generally speaking, as resolution increases, the Chron score decreases. This is perhaps not too surprising. If we look at this spatially, here's all the records in the database, where the hollow symbols are ones with Chron scores that are less than 0 and resolutions that are greater than 100 years. So the filled in circles here are the highest resolution, best age control data in the database, and they're pretty uniformly distributed. There's a bit of a geographic bias. All the ice cores stand out as being high resolution and highly accurate, and there are some clusters other places too. This does give us decent coverage of this sort of stratified portion of the database throughout the Arctic. So one thing that's come up though is how to use this. So, and we're still seeking input and exploring the best ways to use this. So some of the early ideas we had about how we thought this stratifying the database as a function of Chron score would be useful didn't turn out to work the way we thought they would. So we're still exploring some more ideas, but this ChronRater package is available as RCode from my website, and the link to that is also available on the event page. So I really encourage anyone who has ideas about how they might use this for their work to download it and give it a shot and see. And we'd be really interested to hear any feedback about what works and what didn't, and how you used it. So with that, I wanted to say thanks and just remind you that the links both for that white paper and for the ChronRater code are available on the event page, and it's great to hear your feedback. So thank you.
All right, thanks a lot for your talk. I've also pasted the links in the chat, so anyone on the WebEx, if you want to go see the ChronRater package, the software package, or the white paper, you can go to those now, but they are also on the event page, as Nick said, and we will also post them on the YouTube once it is posted. So again, if there's any questions, you can chat them to Research Coordination Networks in the chat window, and I can transfer them to Nick. So we have some questions to get started off here. So you mentioned this is a data synthesis. Who can contribute the data, and how is the data quality addressed?
Are you talking about for which project? For the Arctic Calls?
The first one that you described.
Oh, okay, yeah. So for GeoChronR, so it's not so much a data synthesis as it is a product that's targeted to facilitate quantifying the impacts of age uncertainty in data synthesis. So as part of so the idea is that it would be there'll be this input-output format. This is what this lipid is designed to do, is be a flexible format that can accommodate input. So the idea would be that anyone who wanted to, there'd be as part of the project, we're putting together a baseline database. There'll be a few hundred records and their age models available sort of in the package to start, but we're hoping that the community will be contributing it by putting whatever their data is, whether it's something they're working on or some other published records, into this format, and then adding it in as a way to be able to contribute that data into and use it for the analysis, and also share that with other people who like to be able to use it in whatever questions they're trying to ask. So let's see, and I guess the question is how to do that, and we don't really have a direct way to do that yet. I mean, it won't be. There's not a sense where we're maintaining a public repository for the data that are allowed in there. So essentially, any data can be used in there. Once we have the beta version up a line and people can start uploading data and playing with it. It'd be nice to have some sort of central repository, like I said, like we'll have for the seed database, but the exact plans of how to handle quality control for that have not been fleshed out yet.
All right, great. Yes, you're still beginning. There's still many things to think about. So the next question is, in these projects, have you found that the biggest challenges have been in the cyber infrastructure, the science, or the social aspects of reaching users and getting feedback?
That's a good question. So, in terms of the social aspect of reaching users, we haven't done too much of that yet. So although I do foresee some challenges there, that hasn't been the biggest challenge yet. The biggest challenge for both these projects that I just described is definitely the cyber infrastructure. I mean, the data that went into the Arctic Holocene database, and then getting data, wrangling data to be able to use it in GeoChronR requires an incredible. There's no standardized formats for most paleoclimate data, and there's some for paleoenvironmental, but my focus is more on paleoclimatic. And so each of those records that we want to use or use in one of these packages or put into a database has to be manually wrangled into a useful format. So that's by far been the biggest and most time-consuming challenge.
Okay, and this one is sort of related. Your project is beginning, but is just beginning, but is education and outreach part of the plan? And is there a way that communities like C4P and EarthCube can help?
Yeah, so it's definitely part of the plan. As part of the grant, the Geoinformatics grant, we'll be hosting, not this coming summer, but next summer and summer of 2017, 2 workshops on training early career researchers, so students and postdocs, how to use it. And Julian and I have talked about the idea of doing some webinars for training-based webinars too, although that's a bit more, that's less concrete in the planning. So I guess in both those cases, and there'll certainly be web-based resources for training, there's absolutely room for C4P and other EarthCube activities to increase engagement and exposure to what we're developing and the training opportunities.
Okay, thank you. So I don't see any other questions at this time, but if you do think of some later, I can make sure that Nick gets those. And let's see. Okay, here's the question. It's from Jack Williams. This is a fairly specific question. With respect to resources such as Neotoma, what are the greatest needs for connection?
So connecting Neotoma specifically with GeoChronR is blessedly, compared to a lot of the other things we're trying to do, relatively straightforward because of the way that, I mean, I sort of alluded to the fact that the paleoclimate data aren't very well formatted. Well, Neotoma is sort of the opposite end of the spectrum, where there's a pretty strong structure. There's really nice input-output facilities into R already that Simon Goring's developed. And so integrating GeoChronR with Neotoma should be straightforward, and it's something that we're absolutely planning to do. So in that case, I see a pretty clear and straightforward path to doing that. And I think in the cases of other databases out there that are sort of less well structured and less connected, it's a much bigger challenge.
Okay, so we will be sure to forward the links you have and make sure C4P community has them and has access to them and they're able to give you any feedback. But for now, it looks like there's no more questions. So thank you very much, Nick, for your presentation. So I'm going to pass the screen share over to Yolanda for the second talk now.